Hey, it's May 14th, morning of 2002, or 2020, 2020. Okay, so let's go on. We're moving on. It's Thursday, almost the last day of classes. So let's see, chapter 13 in gases. Hopefully you guys haven't forgotten too much about this. This is pretty close to when we first had to go out and start dealing with all this madness that we're dealing with. So anyway, let's get chapters done. Okay, chapter 13. So why do we study gases? Okay, gases are understanding of how the world works. I mean, we live in gas. Okay, we walk in gas. We're made up of gases. Okay, yeah, it's an understanding how gases work. Okay, you get a really good understanding of how science works. Okay, so real world phenomena. That's what they say. That's basically what's going on all around us, okay? And the science studies, I mean, most of the stuff that we study in science is seriously affected, if not basically derived from or operates upon the world of gases, okay? Oxygen is a gas. Where would we be without that, right? Okay, so anyway, moving on. Okay, so a gas itself. Now, gases, we pretty much... The way that we study gases is, and remember those laws, the Boyle's and Avogadro's and the Charles law and that stuff, the ideal gas law. We kind of study basically how gases react. The volume, it's the volume, it's the whatever it's in. You know, the room that I'm sitting in right now, my studio. It's you know how gas. We study how this volume of this room is of how the gas reacts and what affects it. What, does the volume, change the volume? Yeah, it does. That changes the reaction of gas, right? So that's basically, we're looking at the characteristics of gas, how it reacts in a volume, okay? Whatever the volume is. Don't start thinking of any one single thing. You could sit here and figure out volumes of a glass or whatever, what I'm doing right now. I'm doing right now what I told you not to worry about. It's just the volume, the volume of anything, okay, and how gas reacts in there when it's affected by temperature, pressure, that type of thing, okay. So how much gas, right? The Avogadro's law, the moles of gas, okay, mass, right? So it's all about pressure too. Pressure equals the force. The force put on an area, okay? Force affected by area, okay? And then here are some of the units. Units you're going to, no doubt, if I'm telling you guys, everybody, no matter what degree you go for in college, even if you want to just especially if you want to get like a 2-year degree, would be an LN nurse or something like that, you're going to see this a lot, okay? So blood pressure, it's all about pressure, right? Blood pressure, oh my gosh. Okay, so here are the different units, right? Units. SI units, the standard units are Newton per meter squared. It equals 1 Pascal. Okay, Pascal is very common when we're dealing with pressures. If you go into science, dealing with gases or pressures or anything like that, mechanics especially, mechanical engineering or materials sciences, okay, physics, you name it, okay. Pascal that's 1. It's the standard atmosphere is 101 point, the whole thing. Kilopascals, right? 101,325 pascals. You put that kilo, it makes it a lot easier to write the number down. It's 101.3 kPa. Okay, so I gave you the number bar. That's what you see here in the United States. That's the standard SAE unit is a bar. Okay, you'll hear your weatherman get up and say, the barometric pressure today went from blah, 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 0.987 atmosphere to 685 torr. Okay, so, oh my gosh, torr. Now we know what torr is. Torr is just another measure for atmosphere, okay? So 1 atmosphere is 760 millimeters of mercury, okay, which is equivalent to 760 torr. Okay, it's a lot easier to say torr. Mr. Torr came up with that, and it's a lot easier to use his name, Mr. Torricelli, right, back in 100 years ago, 120 years ago. So, well, even more than that. But anyway, So Torricelli came up with 760 torr equals to the 7 millimeters per of Hg. What is it? Mercury. Okay. 1 standard atmosphere, the pressure that we live in, the world that we live in, 14.7 pounds per square inch. Okay, so that's our standard atmosphere, which is 760 torr, right? So, or it could be 101.325 kilopascals or 101,325 pascals. Did you get that? Or 0.987 atmosphere. Okay, there you go. The barometer was a device used for the early device. Mr. Torricelli was the one that invented this. Okay, the mercury flow, the pressure that's being pushed on from outside the environment. What do you think the pressure is? I bet you it's somewhere around 14.7 psi. Okay, so 14.7 psi will push the mercury that's in this dish, the liquid silver, right? The metal that is liquid at atmosphere at room temperature. Okay. So the pressure outside pushes it up into this tube, 760 millimeters. That's how we know that, and that's 1 atmosphere. Okay, we live in 1 atmosphere. That's our reference. Okay, it changes now. The pressure of atmosphere changes, like at sea level, 760. To be absolutely correct, positive here, to be scientific about it, it's 1 atmosphere is 760 torr at sea level. Okay. If you go up in elevation, that pressure goes down, right? So the higher you get, the less gas is up there. Pressure, so the pressure goes down, right? Volume stays the same, gas goes down, so your pressure goes down, okay? But anyway, 1 atmosphere at sea level will push the mercury that's in this bowl, 760 millimeters, up into this space, okay? Up into this, looks like kind of like a thermometer. It's a meter, right? So this would be a barometer. Okay, so that's measuring. Well, that's with the bar. Okay, forget that. Don't worry about it. So 760 millimeters of mercury. Okay, and Torricelli said, let's just call it torr. Okay, so and that's what happened. Manometer is another way you can kind of, if you change the pressure in your chamber, if you become an engineer or a scientist, like what I did for a living prior to teaching, I worked with pressure, with test devices and actual production devices, okay, systems that the pressure had to be monitored very, very, very precisely, okay, and this is the beginning of how you can start. You know, you put so much pressure into this, and it's going to push the mercury so far, right? An atmospheric pressure. Okay, if you put more gas, more pressure inside this chamber, it's going to push it farther. Okay, and you can measure the distance that it's going to push it. Okay, so and you can get really, really precise. This is a very basic. This is the very early manometer, is what they call it. It's called a manometer. And the manometers that I used in my processes were very technical, very precise, very complex. And the best part of it, though, was the precision. That was critical. I had to be precise with how I set up the pressure in my chamber, the work chamber, where the chips are grown, right? So that's critical. Okay? Talk to anybody who has worked in semiconductor and making microchips, right? And a lot of other processes, too. Just the pressure and gases, and it's all kind of that world when you get into these sciences, okay? So, and here's where you can, you leave this open, heat it up, and get the water boiling inside it, right? Turn it into a gas, close it up, and then as the gas converts back down, condenses back down into a solid, right? Or not a solid, but water right into a liquid, right? The pressure goes down, and voila, there's no pressure on the wall. The pressure that you built up on the chamber of this, on the walls of this can, go away, and it collapses because there's no pressure to get it to keep its shape, and the 14 psi on the outside collapses it. Okay, so here are some conversions. Where are we going? Right, so this is the critical analysis, dimensional analysis stuff, going from atmosphere to torr. We all had to start learning going from atmosphere to Pascal, right? So there are all these different forms of conversion, Okay, and you need to do this stuff when you're doing these gases. Okay, and once again, the PowerPoint has some exercises. The PowerPoint is available to you. Okay, so Boyle's experiment, right? What was Boyle's experiment all about? Okay, observation, moles of gas and temperature. Okay, let's get up to pressure and volume. If one changes, the characteristics inside the chamber. Okay, so Boyle's law was pressure and volume, inversely related. Okay, and then we had Charles' law, which was temperature. You change the temperature and leave the volume set. It's going to change your characteristics in the volume in whatever chamber you're working in, whatever the unit is that you have for measuring volume. Okay, whatever test chamber or room or test tube, whatever. Okay, whatever you're measuring it. Okay, they looked at how temperature plays on the volume. Okay, and if the temperature goes up, volume will go up. Right. And where else are we going here? Avogadro's law. That's what I'm looking at. The amount of gas. Okay, you got volume here. It's nice and happy, right? You insert more gas. You put more gas in there, and your pressure is going to go up. Okay, so it's the more gas, the moles. Moles. What are moles? Moles are molecules of something. Moles are a number. The Avogadro's number is a number, right? So a mole is a number is 6.022 times 10 to the 23rd of whatever gas it is you're dealing with, and that's what that N stands for. Okay. So let's see. Moving on. Okay, Avogadro's law. There's some practicing for Avogadro's law. Okay. You keep these PowerPoints, download them, put them on a thumb drive. Okay. This will be good stuff for you if you come across it again. You can reference this stuff. This is what we've been learning, the basics of chemistry. Okay. And then the ideal gas law is the one where you bring all of the laws together into all the Boyle's, Avogadro's, and Charles' law into one. Okay, and then when you do that though, you have to do this constant. You have to use this R equals this, the universal gas constant. That's what makes it to where you can deal with the variations of all these different characteristics of volume and temperature, and volume and number of number of molecules, moles, right? And then the pressure and the temperature. Okay, so the ideal gas law. And then we went through and we practiced, and it was all about, this stuff wasn't hard, right? Once you get the hang of it. So like I said, I recommend, if I were you, and I did a lot of this stuff. Of course, when I was in high school, we didn't have thumb drives and computers and all that stuff. But all my notes, I just tucked them away. Okay, I would imagine, I bet you have some parents that did the same. So, okay, so practice, more practice, more practice. Okay, and that was it. That was as far as we got. Okay, we didn't get into partial pressures. That was starting to use the applied gases, right? And that would have using the information that we learned. So we didn't have to go that far. So anyway, that is it. You guys work on getting, if any of you have any zeros on those grade sheets, get them cleared up. Okay, and I will talk to you tomorrow. Have a great day.